Okay, so we're going to continue with rational functions here, section 2.6 in our text. We're just going to go a little more advanced here. I want us to keep in mind these are functions with fractions with x in the denominator. Still keep in mind our home base function. This should be ever present when we're talking about rational functions here. Horizontal asymptote, vertical asymptote, domain is everything except 0. That's not going to disappear on us. All right. Today we're going to talk about the two things that we closed with yesterday. We're going to talk about the idea of the numerator having a greater degree than the denominator. We'll hold on to that for 1 second. First, we're going to talk about removable discontinuities and how to locate them, how to recognize just based on the function. All right. So the first function that we're going to talk about, we'll call it f of x. F of x equals the quantity of x squared minus 1 in the numerator and 4x squared plus 8x minus 12 in the denominator. We're going to provide ourselves a rough sketch of this. We're going to talk about domain, as we always do. We're going to talk about vertical asymptotes, horizontal asymptotes. We're going to talk about x-intercepts, y-intercepts. We're now going to introduce this idea of a hole, or a removable discontinuity. So this removable discontinuity is synonymous with a hole in the graph. All right. Some other things that we're going to start talking about again today is the limit as x approaches negative infinity of this function, the limit as x approaches positive infinity of this function. And linked in with that is what we're calling an end behavior model, an EBM, which we introduced yesterday. So where do we start? A lot of different places we could start. If we look at x-intercepts, forever and always we set the y value to 0. So if we have a y value of 0, x squared minus 1 equals 0. We do have a denominator here, but that is pretty quickly going to go away. X squared minus 1, x plus 1, x minus 1. We get two x-intercepts, negative 1 and positive 1. We might need to revisit that in a second. All right. If we were to talk about y-intercepts, x equals 0, so we'd find f of 0 to be negative 1 over negative 12, or a positive 1/12. Definitely not to scale, but we're going to call this point here 0, 1/12. We've got a 1 and a negative 1 there on the x-axis. If we want to start talking about domain and vertical asymptotes, we want to say the denominator cannot equal 0, so 4x squared plus 8x minus 12 cannot equal 0. We'll factor out a 4 as the GCF. Hopefully we can factor further. If we can't factor further, we have to go to the quadratic formula or find another way to find when the denominator equals 0. X plus 3 equals 0 at negative 3, x minus 1 equals 0 at 1, and 4 never equals 0. So don't let that get in your way. We have two vertical asymptotes according to this, and the domain is going to be all real numbers except x cannot equal, what is it, negative 3 and 1. Vertical asymptotes at negative 3 and positive 1. All of a sudden I'm seeing an issue here. I'm seeing an issue that I have an overlap of my vertical asymptote at 1 and an x-intercept at 1. So if I tried to plot this, at 1, supposedly I'm crossing the x-axis, but also at 1, supposedly I have a vertical asymptote. I don't see how that's possible to have a vertical asymptote and cross the x-axis. One thing we should go back to, and maybe this is where we should have started, is we should have factored the numerator and the denominator, which we did over here on the side. But one thing we would see is that in the numerator and in the denominator, we have this factor, x minus 1 here, not x plus 1. We have a factor of x minus 1. We also have an x plus 1 in the numerator. But in the denominator, x plus 3, and this factor of 4. But the x minus 1 is going to create this removable discontinuity, or this hole that's located at 1 something. And we'll figure out that something here in a second. But we should delete -1 from our list of vertical asymptotes. Positive 1. We should also delete +1 from our list of x-intercepts, because it's neither a vertical asymptote nor an x-intercept. When it can't be both, it's not going to be either. It's going to be a hole there. Let's put on here this idea of the vertical asymptote at x equals -3. But at the same time, let's erase this vertical asymptote at 1, and we're also going to erase the x-intercept there at +1. Last thing, horizontal asymptote, the limits to the left and right, the end behavior model, all of this stuff is related. So to discuss those, we're going to discuss the end behavior model is going to be governed by x squared over 4x squared, which simplifies to 1/4. My end behavior model is going to be y equals 1/4. My horizontal asymptote will be y equals 1/4. Way out to the left, my graph is going to approach 1/4. Way out to the right, my graph is going to approach 1/4. So I've got this positive value. I should probably draw that above 1/12. We've got 1/4 and 1/4. Now, how do we connect the dots here to draw the entirety of this graph? If I've got this end behavior of going out to 1/4 on the left, I'm going to approach this vertical asymptote with -3. I've got two choices. I can either go up or I can go down. To decide that, I need to look at other features. The key feature that I would say is if I went down, I would have to cross the x-axis here, and according to my x-intercepts, I'm not crossing the x-axis anywhere to the left of -3, so I'm going to determine that I'm going to have to travel up. Yesterday we discovered that 99% of the time, if we go up on one side of the vertical asymptote, we're going to travel down on the other. We'll connect our dots, we'll connect our end behavior. And we get a graph like this, with one exception. Instead of being continuous here, we're going to have a hole. And that hole is going to be located at an x value of 1. The only remaining thing that we need to determine is how to find the y value of that hole. Right? I'm probably going to guess that it's going to be between a y value of 1/12 and a y value of 1/4, but I don't know that for sure. So how do I locate that hole? I locate that hole by plugging in 1 into my f function. Right? So I'm going to find f of 0. However, I am going to do that after I remove the common factors. So I'm going to take out that x minus 1, because if I left it in there, when I plug in 1, I'd get 0 over 0. I don't want that. So I'm going to go 1 plus 1 over 1 plus 3 times 4. 4 times 4 with a 2 in the numerator, I've got 2 over 16. I'm going to get a y value of 1/8. My hole is located at 1, 1/8. If you have questions with how any of that occurred, make sure you're jotting that down at this time so that tomorrow you can bring up those questions in class. We're going to go through one other function. This function we'll call g of x. And g of x will be x cubed minus 3x squared minus 4x plus 12, all in the numerator. And then my denominator is going to be x plus 1. We discussed in the last problem that maybe a good first step before we get into anything is let's factor. All right, I think I'm going to factor the numerator here by grouping. I'm going to take out an x squared. I'll be left with an x minus 3. I'm going to take out a negative 4. I'm going to be left with x minus 3. I'm excited about that. I have that common factor of x minus 3. I then also have an additional factor of x squared minus 4 in the numerator. X plus 1 is still in the denominator. I can take the numerator one step further, x plus 2, x minus 2. I should recognize pretty quickly that this function will not have a whole. This function does not have a common factor in the numerator and denominator. That's going to be ruled out. We're going to talk about the x-intercepts, the y-intercepts, the domain, vertical asymptote, horizontal asymptote, whole, the limit as x approaches negative infinity, this time of g of x, the limit as x approaches positive infinity of g of x, and the end behavior model. Right, those are going to play a bigger role here. But one thing we just said, the whole, non-existent. It's not going to be there. I don't know exactly where to start, but I'll start with something that I find easy. Denominator cannot equal 0. That's going to help me set the vertical asymptote. That's going to help me set the domain. So x plus 1 can't equal 0, so x cannot equal negative 1. My domain, all real numbers, except x cannot equal negative 1. Vertical asymptote at x equals negative 1. We'll dot that on here. Vertical asymptote, x equals negative 1. From there, where do we go? Really your choice. X-intercepts, we're going to set y to 0 and y equals 0. All we really care about is the numerator equaling 0. It's nice that we already have this factor, and we can find three values here of where we're going to be negative 2, positive 2, and positive 3. We can see that none of those overlap with vertical asymptotes, so we don't have the whole. Negative 2, positive 2, positive 3. Y-intercept, we're going to set we're going to set x equal to 0. So we're going to find g of 0. This is going to wind up giving us a 12 over 1, which is 12. What else do we need? Oh, so now the last thing that's left, we need to discuss this horizontal asymptote, the limits way out to the right, the end behavior model. So if I'm going to discuss the end behavior model, I'm going to look at the x cubed over the x. This is our scenario where the numerator is larger than the denominator. This is going to simplify to y equals x squared. Alright, y equals x squared. What we're saying there is that our function g of x, that's not what we do. Our function g of x and x squared, the further out we get, the more and more alike they're going to be. Alright. They're not exactly the same, but they're going to become very, very similar. All right. So what does x squared do way out to the left? It goes up to positive infinity. What does x squared do way out to the right? It goes up to positive infinity. If my graph is going to go up to positive infinity in both directions and not flatten out, well, what's that mean for a horizontal asymptote? It means there is not a horizontal asymptote. So if we connect the dots with the end behavior, we're going to cross through the x-axis. We're going to come down 99% of the time. We're going to start on the other side. Cross, cross, and come up. All right. This is a rough sketch here of g of x. If you have any questions about g of x, hold on to those. Make sure that those are discussed in class tomorrow. The two concepts that I want us thinking about moving forward, and maybe you can explore on your own, is instead of a horizontal asymptote. All right, so that might be something that you explore in your text or explore in your own study. The other thing would be all of our x-intercepts so far have crossed the x-axis. When do x-intercepts bounce? Can that happen with rational functions? Is that possible? What would that look like, and what in the function would tell us that occurs? All right. I'm going to leave you here with an image of this actual function from g of x, a better graph than my rough sketch there. So here it is. If we look over here on the left, I have g of x plugged in. I can zoom in and out to see this. I do indeed have an x-axis crossing at -2, +2, and 3. I am going to have an asymptote of x equals -1. I don't have a horizontal asymptote. I also have over here e of x equals x squared minus 4x, which is a parabola that looks like this. The further I zoom out, the red and the blue look more and more identical. That's something to hold on to for tomorrow as we discuss slant asymptotes. How did I get that x squared minus 4x rather than just x squared as we had discussed over here for the end behavior model? All right, take care.